Okay, today we start a new chapter, integration, multiple integration. This continues the arc of the semester where we first learned about vectors and planes and so forth. Then we moved into differentiation of functions of several variables, and now we're doing integration of functions of several variables. This is the penultimate chapter. In the final chapter, what we'll do is we'll connect differentiation and integration in the multivariable context, and this is akin to what you did in Calc 2, where you learned the fundamental theorem of calculus, which connects differentiation and integration. It turns out that there are some really deep connections between differentiation and integration in calculus of several variables. But that's for later. For now, we're going to start by talking about the simplest form of multiple integration. We're going to integrate functions of two variables over rectangular regions in the domain. The very smallest part of this section, honestly, is calculating double integrals over rectangular domains, because the process is relatively straightforward and it's one that you've already got the skill sets for. I'm much more interested in the Riemann sum definition of the double integral and how we can use that to approximate answers to questions that we might have about real applications. And honestly, in statistics, in engineering, in physics, and in many other applications, it's approximations of double and triple integrals that actually matter. It's extremely rare that you encounter a situation where you can actually do the integration and get an exact result. Much more interesting, much more useful is the Riemann sum and the approximating of double integrals. Another aspect of this section, and this is a somewhat, there are actually, for an introductory section, there's a lot going on here. Another really important aspect is the collections of properties of double integrals, and we'll talk a little bit about that too. The properties of double integrals are more useful for later theoretical work that involves multiple integrals. So we've got sort of two prongs here. Approximating double integrals using Riemann sums, which is useful for applications, and we've got applying these more theoretical properties of double integrals, which is going to be useful for later theory. And again, the smallest bit of this section is the actual calculation of double integrals, and I'm going to leave that mostly to you. The big goals here are to recognize when a function is integrable over a rectangular region, to recognize and use some of the properties of double integrals, evaluate double integrals, and use double integrals to calculate the area of a region and the volume under a surface, or the average value of a function over a plane region. I think the big idea here is that double integrals compute the volume under a surface above a rectangular region. The other thing that we're going to discover is something called Fubini's theorem. We've got two variables here. We've got an x and y variable in double integrals, and the mechanics of integrating are going to have us integrating with respect to one variable and keeping the other variable fixed, and then integrating with respect to the other variable. And Fubini's theorem tells us that it doesn't matter which order we do that. We're going to learn that it's possible to compute the average of a function of two variables by computing the double integral over the region and then dividing by the area of the region. We will learn that it's possible to compute the area of a region of integration simply by integrating the constant function 1 over the region. That'll give us the area. That's super useful in theoretical applications. And the last big idea is that in most applications we're using Riemann sums to approximate double integrals. We're not actually doing them exactly. Jumping over to the flyover of the text, I'm not going to spend a whole lot of time on this because I think mostly you're going to learn how to do this stuff by example. Um, the idea here is we've got this rectangular region underneath this surface, or I think probably better put that the surface sits above this rectangular region in its domain. It's important to kind of adopt a standard notation as we work through this. The limits of this rectangle, or the width of this rectangle in the x direction, is going to go from A to B, and in the y direction from C to D. And we're always going to use A to B in the x direction, C to D in the y direction. The surface as it sits above this rectangle is the function z equals f of x and y. And what we're going to do is we're going to take that rectangle. Now we're looking at the domain, and the surface is sort of somewhere else. We're going to take that rectangle and chop it up into pieces. We're going to chop it up into m pieces in the x direction and n pieces in the y direction. And we're always going to chop it up into an even number of pieces. So we're not going to have some narrow rectangles and then some wide rectangles. They're always the same width and they're always the same height. Doing that, you can see here we've chopped up the domain into nice uniform collection of little rectangles. Above each rectangle, what we're going to do is we're going to pick a point inside the rectangle, and we're going to compute the height up to the surface. And we're going to build a rectangle that sits underneath the surface that's as high as this point. And we can easily compute the volume of that rectangle as just the area of the base times the height. And you can probably see where this is going, akin to what you learned in Calc 2 with Riemann sums. If I sum up the volumes of all of these rectangular columns over the region R, I'm going to get a pretty nice approximation of the volume underneath the surface over the entire rectangle. That's the big idea here. And that leads to this definition. The double integral of f over the region R, given by this notation, R here sits beneath these double integral signs. F of x and y, the integrand, is the function that we're integrating, and dA is a little piece of area, and I think the best way to think about it is it's the area of the base of one of these rectangles. That is the limit as m and n go to infinity of this double sum. And what's important here, this limiting process is really just describing the process of making a finer and finer mesh in this rectangular region and getting a better and better collection of approximating volumes, these rectangular columns. The xij star yij star is really just any point inside this little rectangular base of one of the columns. It's any point, and you'll see later that we'll specify, sometimes we'll use the midpoint to compute the height, sometimes we'll use the lower left corner, sometimes we'll use the upper right corner, sometimes we won't specify it at all, and it turns out to not matter, because as we let m and n go to infinity, that base becomes so small it doesn't really matter where you choose the sample point. And that's what this is called, the sample point. And the sample point is used to compute the height of the rectangle. If you look at this summand here, this thing underneath the double sum, f of x star y star is the height of the rectangle, and delta A is just the delta x times the delta y is the area of the base. And multiplied together, what we get is the volume of this column. Okay, here we see an example of setting up a double integral and approximating it by double sums. So we're going to think about this function 3x squared minus y over the rectangular region 0, 2 cross 0, 2. This is some new notation that perhaps you haven't seen before. We're talking about x is always in the first position, y is always in the second position. This is consistent with ordered pairs x, y. What this is telling me is that in the x position, this rectangle goes from 0 in the x direction to 2 in the x direction, and it goes from 0 in the y direction to 2 in the y direction. So this is essentially a 2 by 2 square with the lower left corner sitting at the origin. That's the rectangular region. If we look at it here in this diagram, we see here's the lower left corner sitting at 0, 0, 0 in the x direction, 0 in the y direction. And we're looking at this surface, 3x squared minus y over this rectangular domain. So we set up the double integral for finding this thing just using the notation. That's all that means. And then we're asked to approximate this with m equals n equals 2. So that means chopping the interval from 0 to 2 into two pieces and chopping the interval from 0 to 2 in the y direction into two pieces. This divides R into 4 squares, and then we're going to use the sample point as the upper right corner of each square. That leads to this collection of points. And then we simply plug them into this double sum, not taking m and n to infinity, but rather just m equals 2, n equals 2, and compute the approximation. So the double integral over the region looks like this. Approximating the signed volume using m equals n equals 2 gives this diagram. Using the upper right corner of each of these subrectangles for the sample point will give us the height of each of these rectangular columns. Plugging all of those values into the double sum gives 24. And if you were to do this thing exactly, which we'll talk about in a minute, you would get presumably a number close to 24, although maybe not such a great number, because using just two subintervals and using the upper right point as the sample point is not the best strategy for getting a good approximation. Okay, let's keep going. Properties of double integrals. So the double integral distributes across addition. In other words, the double integral of the sum is the sum of the double integrals. Constants can move freely in and out of the double integral. This is a little bit weird, but if you have a domain R, a rectangular domain R, that is actually the union of two other rectangular domains, and those two other domains don't intersect, then the integral over R is just the sum of the integrals over S and the integral over T. Properties 4 and 5 are really important. If f is bigger than g on the rectangular region R, then the double integral of f is going to be bigger than the double integral of g over R. If f is bounded above by a constant and below by another constant on the rectangular region R, then the integral is going to be bounded above by the upper bound times the area and bounded below by the lower bound times the area. Also a really important idea for approximating integrals. Finally, if f can be written as the product of a function solely of x and a function solely of y, then you can take the double integral and actually separate it out into two single integrals. In the event that you can't do this, turn it into two single integrals, we have a different approach for computing double integrals called iterated integration. And iterated integration says if I have a double integral like this over a rectangular region, it suffices to just integrate with respect to y, treating x as a constant, and then taking that result and integrating with respect to x. And it also turns out it doesn't matter which order I do it. I can do dy and then dx, working from the inside out, or I can do dx and then dy, working from the inside out. The important thing to remember is if you switch the order of integration, so the order of integration is determined by these symbols. Dy dx means do y first and then x. If you switch these, in other words, do dx and then dy, don't forget to switch the integrals. So notice the first integration is with respect to y, we're integrating from c to d. Here the first integration is with respect to x, we're integrating from a to b. So when you switch the order of integration, don't forget to switch the limits of integration, the two integrals. Fubini's theorem is again just telling us that these double integrals are equal to the iterated integrals, and that it doesn't matter which order you integrate. There's a nice diagram here that's maybe worth thinking about. Iterated integration is really for a fixed y. So let's say we're integrating with respect to x first. What that gives me is the area of the cross section of the volume for a fixed y. And then what we do is we sum in the y direction to collect those areas to compute the volume. Once you see this picture, you acknowledge that it shouldn't matter whether I sum up cross sections along the x direction or cross sections along the y direction. In the end, I'm going to get the same volume, and that's essentially the heart of Fubini's theorem. Using Fubini's theorem, we have, for example, this double integral, which is just the simple function x over the interval 0 to 2, 0 to 1. This determines the limits in the x direction. This determines the limits in the y direction. This determines the integrand. So the double integral here is 0 to 2. If we're going to integrate with respect to x first, we go 0 to 2 in the x direction and then 0 to 1 in the y direction. We don't have to put x equals, y equals here. It's just emphasizing that these limits are in the x and y directions respectively. We do the x integral first, meaning we integrate the integrand with respect to x, holding y constant. There's no y here, so that's not important. Integrating x, we get x squared over 2. Plugging in 2 and 0, we get 2. And then we do the second integral, the outer integral with respect to y. Integrating 2 with respect to y, we get 2y. Plugging in 1 and 0, we get 2. That's iterated integration, and that's probably the least important aspect of this section. I'm going to trust you to practice and get that, that skill down. More interesting is illustrating the various properties. Up above, there were these 5 properties. Illustrating properties 1 and 2, this is the fact that integration distributes across addition and that constants can move in and out of the integral. Let's look at this double integral over the region. Here's another way of writing a rectangular region. Here we see the x limits go from 0 to 2, the y limits go from 1 to 2. Let's integrate with respect to x first, and we're going to write the double integral first. The double integral over r of this thing distributes onto each of these terms. And then furthermore, we could pull the minus sign out, or we could even pull the 3 out if we wanted to. We do the inner integral here with respect to x, and then with respect to y, and in the end we get minus 11. So again, just a little bit more practice on doing these kinds of integrations. Illustrating property 5. Property 5 is, let me remind you what property 5 is and remind myself. Property 5 is the one about the bounds. So if f is bounded between 2 constants on the rectangular region, then we have these results. And down here, property 5, we have e to the y cosine x over this region where x goes from 0 to pi over 2 and y goes from 0 to 1. What we see here is, here we're computing it directly. Oh, this is property 6, excuse me. So this is a separable function, a function solely of y times a function solely of x, which means we can separate it into 2 ordinary integrals. Pardon me. Okay, evaluating an iterated integral in 2 ways. This is just integrating with respect to y, then with respect to x, or x and then with respect to y. Believe it or not, this sometimes has a purpose. There are some integrals where it's easy to integrate in one order and impossible to integrate in the other order, and you should just be aware that you can get yourself out of a jam simply by reversing the order of integration, since Fubini says that doesn't matter, you get the same result. So I'll let you look at that example. Switching the order of integration, yes. Applications of double integrals. The area of a region R is given by just the integral of the constant function 1 over the region. This makes sense because for the constant function 1, all of the columns have height 1, And so the area of the base times the height is really just the area of the base, and then the integral is going to add up all of those bases, and you'll get the area of the entire region. And this important result not only works for rectangular regions, but it works for arbitrary regions, which we'll learn about in the next section. And finally, we have the integral average, where we can integrate a function over its region and divide by the area of the region, and we get f average, the average value of the function over this region. And we'll talk a little bit about applications here. I've got at least one application at the end here, so I'll let you look at that example, and we're now ready to talk about some of these exercises at the end. Okay, let's jump over to the notes here and start working through some of these exercises. In the following exercises, you're asked to use the midpoint rule with m equals 4, so that's 4 subintervals in the x direction, 2 in the y direction, to estimate the volume of the solid bounded by the surface above, the vertical planes x equals 1, y equals 2, and the vertical planes y equals 1, y equals 2, and the horizontal plane z equals 0. Boy, that's a ton of information. Let's work through that. This is pretty typical of how you'll be, how these problems are described. Let me start first by looking at the domain here. So I don't want to use black. I don't want to use red. Okay, so we have, let's see, from 1 to 2. So these vertical planes, they're really just telling you 1, 2, 3, 4, 1, 2, 3, 4. There's 1, there's 2, and then let's go here and here. Also 1 and 2. All right, so imagine that you had a vertical plane here and here at x equals 1, x equals 2, and you had a vertical plane here at y equals 1 and y equals 2. Those vertical planes would naturally carve out a rectangular region in the xy plane. And remember that we have the surface z equals f of xy sitting up above, all right, or below, somewhere. We want to use the midpoint rule to approximate or estimate the volume of the surface, the volume under the surface and above this rectangle. Now, when we have, let's see, m equals 4, that means we're going to chop up this interval into 4 equal pieces. Let me get rid of this, this, and this. We're going to chop up this interval into 4 equal pieces. In fact, let me use a different color. Okay, so 1, 2, 3, 4 equal pieces. And horizontally, we're going to chop it up into 2 equal pieces, like that. So we have these 8 subrectangles, and we're going to use the midpoint rule as our sample point. So here, 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 like that. Those are our sample points. And then what are we going to do? We're going to simply fill in I equals, let's see, 1 to 4, j equals 1 to 2, so 4 is m, n is 2. The sample points, f, x, I, j star, these are the midpoints of each of the subrectangles, which we have not computed, so we're just going to use the symbols. And then times the area of each subrectangle. Okay, we can figure this one out. We took the interval from 1 to 2 and we divided it into 4 equal pieces. The interval from 1 to 2 is of length 1, And so delta x here is 2 minus 1 divided by the number that you chopped it up into, 4. So each subrectangle has base width 1/4, and similarly delta y, remember we took the length of that interval and chopped it up into 2 pieces, so 1/2, and the area of the base of one of these things is just delta x, the width, times delta y, the height, which is 1/8. And we can take that and put it in up here. And so the approximate integral over this region R of f dA is represented by this sum, and we can put 1/8 up in here. You could certainly go through and calculate this on a calculator. For example, we see here if we chop this up into 4 pieces, this is 1.25, 1.5, 1.75. This is 1, 1.5, and 2 up there. And we could compute the coordinates of each of these green dots and plug them in here, add them all up, multiply by 1/8, and we would get the approximation. I've taken the liberty actually of creating a little program in CoCalc in Sage that will take in all of these parameters, m, n, f, etc., and compute the Riemann sum approximation for you. If you want to use this instead of doing this by hand and doing it on a calculator, you're welcome to do so, and there's a link to the worksheet that you can download and then upload into your Sage account to help you do these calculations. So I'm going to jump over to Sage and show you how to use this little program on this example number 2. So what I've done is I've written this little program called Riemann sum approximations of double integrals, and between these two lines of hash marks, all of the information that you need to do the Riemann sum approximation is there. So in this section, I'm asking you to define the limits in the x direction. Here, the limits in the x direction are from 1 to 2. So I'll replace a with 1 and b with 2. The limits in the y direction were also 1 to 2. So replacing c with 1 and d with 2. The number of subintervals in the x direction was 4. Remember, m is always for the x direction, and n is always for the y direction. In this case, n is equal to 2. What kind of sample point location are we using? Lower left, upper right, midpoint? We're using midpoint. Let's see, use the midpoint rule, it says right here. So for this little program, if I say quote MP end quote, that will tell the program to use the midpoint. And finally, the function to integrate is 16x squared plus y over 2. So I'm going to replace this with 16x squared plus y over 2. And let me double check, that looks good. Nothing after this second line of hashes is necessary. And when you're ready, with the cursor anywhere inside the program, hit Shift Enter, and at the bottom you get a decimal approximation of the double integral using these parameters. In this case, it turns out to be 38. So this is approximately 38. Now, the problem doesn't ask for it, but we can actually do this integral with these limits of integration exactly. So let's do that. And I've got this extra line at the bottom. Check against the actual answer if possible. There are some integrals that even Sage can't do, but this is one that Sage can handle. So we put the cursor on this line, we hit Shift Enter, and it takes f and integrates with respect to x from a to b, and then with respect to y from c to d. two integrate commands because it's a double integral, we get 38.08, which is pretty darn close to 38. So even with this relatively coarse approximation, we get good results. It's not always the case. Here we're asked to estimate the volume under the surface and above the rectangular region by a Riemann sum, m equals n equals 2, and use the sample points to be the lower left corners of the region, of the subrectangles, excuse me. All right, so once again, I'm going to defer you to the program. You could do this by hand if you wanted to, but I'm letting you use the program because it's convenient and it's how things are done in actuality. So let's go and repeat the exercise. We'll read carefully through the parameters. We've got the x direction goes from 0 to pi, so I'll replace a with 0 and b with pi. The y direction goes from 0 to pi over 2, 0, pi over 2. The number of subintervals is 2 in the x direction and 2 in the y direction. We are supposed to use, let's see here, lower left corners, so I'm going to use LL here. And then finally, the function to integrate is cosine x plus cosine y. Cosine x plus cosine y. And that's the end of the parameters that are needed to run the function. Hit Shift Enter, and we get 9.86, whatever that means. And again, this is an integral that Sage can actually do exactly. And wow, that seems wrong, but who knows? All that looks good, so I guess I'll take my word for it, or take its word for it. This could be a case of a really terrible sample point. Let's try a different sample point. Let's try midpoint. Okay, when I do the midpoint approximation, the decimal I get out is 9.9, and you think, well, that's not close to 0 either, but be careful. E minus 16 means that this is 9.9 times 10 to the minus 16. That's a really small number. That's close enough to 0 that I feel good about that. So the midpoint approximation does a really nice job of approximating, whereas the lower left approximation does a terrible job. And that's because midpoint is generally when you use the midpoint, any kind of variation in the function usually is sort of a little bit above and a little bit below, and you get some nice cancellation of the error and things work out well. Whereas when you use lower left or upper right, depending on the kind of function, you could be doing a gross overestimate or a gross underestimate. So midpoint's generally the best sample point location. That said, if you take the limit and let m and n get really large, then it doesn't matter. For really large number of columns of rectangles, you're good. In fact, we can see that here if we crank up the number of rectangles. Let's go, instead of 2 in each direction, let's do 20 in each direction. Doing 20 in each direction, better, not great, but certainly closer to the 0 that we expect. We could do 200 in each direction. This might take a while to run, I don't know. 200, right? Double sum, 200 times 200, that's like what, 40,000? We'll see how long it takes my poor little computer to do this work. Apparently it's going to take a really long time, so let's just let that go there for a while. Back over here, we found that the approximation was terrible for lower left. It was around 9.8 for lower left, which was terrible. But it was around 0 for midpoint, which was pretty good. So the midpoint approximation is better. Okay, the lower left approximation, even with 200 subintervals in each direction for a total of 40,000 subintervals, still only gets us down to 0.09, really rounds to 0.1. So this is an important area of application, one that we're not going to talk about right now, but the sample point can matter. All right, in problem 8, we're given we've got this hole. It's a 3-foot by 3-foot rectangular hole in the ground, and it's been measured at 1-foot intervals. So, for example, starting at x equals 0, I drop a line down into the hole and I see, oh, the line's 6 feet long when it hits the bottom. And then I move over a foot in the y direction, still x equals 0. I drop it down and hey, the line goes a half a foot deeper, 6.5. Another foot, 6.4. Another foot, back to 6. Then I step over in the x direction 1 foot and I repeat the process. I drop my line down, it hits the bottom at 6.5, then it hits the bottom at 7, 7.5, and so on. And I repeat this process and I form a grid of sample points. And what you're asked to do is estimate the volume of the hole by using a Riemann sum with m equals n equals 3 and sample points to be the upper left corners of the subsquares of R. I'm going to do a little bit of transformation here, or draw a little bit better picture here, because we're kind of used to looking at the XY axis in this configuration, and we've got sample points at the red dots in the X direction and then at the red dots in the Y direction, like that. So 0 to 3 in both directions. What do these sample points look like? Well, at x equals 0, y equals 0, we've got a 6, and then we've got a 6.5, and so on, up the line. All right, so where are the subrectangles? The subrectangles in this rectangular domain are here. And where are the upper left corners? The upper left corners are here for this, and then here, and then here. So we're going to completely ignore the last column of values. All right, so the upper left corner, the first sample point is going to be x equals 0 and y equals 1. So we're going to use this guy, and then y equals 2 and y equals 3. And then we're going to use 0, 1, and 2. So we'll use 0, 1, and 2 in the x direction and 1, 2, and 3 in the y direction. Which values does that correspond to? That corresponds to this collection of values right here. I always have to draw a picture when I'm given a table of values and asked to use a particular sample method. Once you have the sample method, then we're ready to fill in the double sum. The double sum goes from I equals 1 to 3, j equals 1 to 3, f, x, I, j star, this is the sample point using upper left, y, I, j star, times delta A, the area. What's the area of one of these rectangles? It's 1 foot by 1 foot, so the area here is just 1 foot squared, 1 square foot. So we don't care about the 1, and what do we need to do? We just need to sum up this collection of points. So to do this approximation, it's 6.5, 6.46 plus 7, 7.5, and 6.5, and finally plus 6.7, 6.5, and 6. And I've taken the liberty of adding these up in advance, and what do we get? We get 59.1, and that's cubic feet. So that's the approximate volume of the hole. Find the average depth of the hole. How do we do that? So what we're going to do is take the approximation of the double integral. So we've done the approximation over the region R of the volume function. I don't know, let's just call it f of x and y dA, and we found that it was about 59.1 cubic feet. And if we want to compute the average, we just need to divide by the area of R. What's the area of this rectangle? It's 3 times 3, 9 feet squared. And we get 59.1 over 9, which turns out to be 6.56 repeating, and the units are feet, which makes sense. So that's the average depth of the hole. All right, another way of approximating double integrals is to use level curves. So here we're given not an explicit function, but rather we're given the level curves of some mysterious function, and we're given the values of those level curves. So for example, along this level curve, f is equal to 1/32. Along this level curve, f is equal to 1/16, and they're in order. So this one, this one, this one, here, here, here. All right, so we can quickly kind of identify approximate function values along this contour map. All right, you're asked to apply the midpoint rule with m equals n equals 2 to estimate the double integral over this over this rectangular region. So from point 1 to point 5, so from here to here, and then point 1 to point 5 from here to here. So as a subrectangle, or as a rectangular region, we're looking at something like this. And then we're asked to chop it up into 2 pieces in the x direction and 2 pieces in the y direction. And then finally, we're asked to use the midpoint rule. So let's mark our points here using the midpoint rule. Let's eyeball it there, and the midpoint of that region there, and the midpoint of that region there. And now we have to do a little bit of approximation. So for example, this midpoint seems to be right on this line. So the first midpoint, let's label these in no particular order. Let's call them, whoops, apologies here. Let's label them 1, 2, 3, and 4. Okay. For value 1, we've got to look at the contour map and try to figure out what the height of the surface is at that point. This midpoint lands almost right on the level curve for 1/16, so I'm just going to say, you know what, that's 1/16. Okay, let's look at 2. If you look at 2, it seems to kind of be moving, it seems to be sort of halfway between this level curve, which is 1/8, and this level curve, which is 1/4. So for 2, I'm going to say that's about the average, 1/8 and 1/4. Like that. Okay, that works out to be, let's see here, oh good lord, 1/8 plus 2/8, 3/8 over 2, 3/16. Number 3, oh boy, so that's kind of on this line here between, I'm going to say 1/4 and 1/2, somewhere between 1/4 and 1/2. And you know, this is actually a pretty challenging idea. It's between, what did we say? Between 1/4 and 1/2, right? And if I were sort of looking at this, I would say it's maybe 1/5 of the way on this line. It's about 1/5 of the way from the 1/4 mark to the 1/2 mark. Well, what is the total change here? We're just going to kind of approximate here. How much does it change as it goes from this blue line to this red line? It goes from 1/4 to 1/2. So that's a net change of 1/4 to 1/2. That's a net change of 1/4. And what I'm saying is it does about 1/5 of that change. So I'm going to multiply that by 1/5 to get 1/20th. All right, so I'm saying by virtue of having moved this far along from the 1/4 line to the 1/2 line, I've gained about 1/20th on the 1/4 line. So I'm going to approximate this to be 1/4 plus 1/20th. Let's see, that's 5 6/20ths, 3/10ths. So we're going to say that the third one is 3/10ths, and finally the fourth one. The fourth one's not bad. It looks like it's sort of smack in the middle between the 1/8 and the 1/4 line. So we can use, in fact, it's very much like number 2. So we're going to say that's 3/16ths because it's a lot like number 2. Alrighty, let's see, what have we done here? We've got the values of f at all the sample points. Cool. We need the area of one of these subrectangles. All right, the area of a subrectangle is the distance in the x direction of one of the subrectangles. So let's see, we went from point 1 to point 5, so that's 0.4, and we have 2 subintervals, so that's 0.2 in the x direction. And then similarly in the y direction, also 0.2. That works out to be 0.04 in area. And we're now ready to compute the Riemann sum approximation here. Let me give myself a little more space. So what do? We have the Riemann sum over R of this function, dA, is about or approximately 1/16 plus 3/16 plus 3/10 plus 3/16 times 0.04. I can plug that into Sage or something similar. Let's go to Sage and just do it real quick here. So we want the decimal approximation of 0.04 times 1/16 plus 3/16 plus 3/10 plus 3/16. And that gives us 0.0295. Like that. And let me check my notes here and see if we're even in the ballpark. Oh, we don't have answers for this one, so yeah, so there you go. So we drew the grid onto the domain and we used the level curves to approximate the value of the function at the various sample points. Plugged all that into the double Riemann sum, and we ended up with an approximation of the double integral of 0.0295. Okay, In the following exercise, we want to compute the iterated integral by choosing the order of integration. This particular example, it doesn't really matter. Pick an order of integration. We can use the order of integration that we've been given, or we could choose to reverse the order of integration. Let me check my notes here and see what I decided to do. Looks like I just kept the order of integration that I was given. So we do the inner integral first. The inner integral is just an ordinary integral from 1 to 2 of y over x plus y squared dy. You can do this by u substitution. If you let u equal x plus y squared, du is 2y dy. And if you plug all of that in, let's see, 2y dy is what, 1/2 integral du over u. That looks good. Yep. And when when y is equal to 1, u is equal to x plus 1. And when y is equal to 2, u is equal to x plus 4. So there's the new integral. We can anti-differentiate, and we get the natural log of u, and we evaluate from x plus 1 to x plus 4, which yields 1/2 the natural log of x plus 4 minus 1/2 the natural log of x plus 1. What do we do now? We do the outer integral, and that's with respect to x, and we integrate from 0 to 1 of 1/2 ln x plus 4 minus ln x plus 1 dx, like that. And you may or may not remember it, but there's a formula for the antiderivative of the natural log. Up here, let me just note that the antiderivative of the natural log of u is u times natural log of u minus u. So doing that gives us 1/2. We integrate natural log of x plus 4. Technically there's a u substitution there, but I think we can handle that. X plus 4 natural log of x plus 4 minus x plus 4 minus x plus 1 natural log of x plus 1 plus x plus 1, and all of that is from 0 to 1. If you plug in 1, you plug in 0, and you simplify, you're going to end up with, well, here's an intermediate result. Working with natural logs can be a little bit challenging. If you work it out, you'll end up here. And then, as per usual, I went over to Sage to check this calculation because, you know, it gets kind of dicey, and I got something a little bit different. And so whenever you're working with natural logs, sometimes when you check the answer in the back of the book, it doesn't match, and that's because there's some sort of log simplification going on. And there's some log simplification that we can conduct here. I'm sorry, I got 4 log 4 here. Minus 2 log 2. So a bit of a trick here. 4 is secretly 2 squared, and we can bring that 2 out front to get minus 8 natural log of 2, and then 2 natural log of 2. Those two join to become negative 10 natural log of 2, and then we can run the 1/2 in. 5/2 natural log of 5 minus 5 natural log of 2. So that's the iterated integral. You might check, as an exercise, check integration in the other direction. you should get the same answer. All right, let's find the average value of the function over the given rectangles. Gosh, I'm not sure why I have that there, because that's unrelated to this problem 39. So I'm going to just delete that and move on. Okay, problem 39. F and G are continuous functions bounded above and below like this, and they're both positive. Show that the following inequality is true. So this is a bit of a theory question. Now, whenever you have an inequality like this, sort of a string of inequalities, they're really two separate problems. So you have to address this inequality and then address this inequality. I'll do this inequality and then I'll leave it to you to kind of understand how to do the other inequality. So let's see here. We're looking at the integral from a to b, integral from c to d, f of x, g of y, dy, dx. And what we see here is that this is one of these separable integrands. In other words, the integrand is the product of a function solely of x and the product of a function solely of y. So we can separate this into two regular Calc 1 integrals and multiply them together. Like that. And knowing that f is bounded above by m1, we know that this first integral is less than or equal to m1 times b minus a. And knowing that g is bounded above by m2, the second integral is bounded above by m2 times d minus c. And that's precisely the upper bound that you're looking for. You can do the same thing with lower bounds. How do we know, oops, this is not equals, this is less than or equal. How do we know this result? This is a result from back in Calc 2. If the integrand was bounded above by a constant, then the integral was bounded above by that constant times the length of the subinterval. All right, in this exercise, you're asked to use property 5 of double integrals to kind of wrestle with this problem. And you can use the answer to the preceding exercise also. Notice this applied to functions that were positive and bounded above and below, and an integrand as a function solely of x times a function solely of y. That's what we have here, a function solely of x times a function solely of y. So this, oh, and there's a typo here. This should be quantity squared here. So we can write this integral by first noting that e to the minus y is bigger than or equal to 0 and less than or equal to 1 on the interval 0 to pi over 2. And we can also note that the cosine of x is bigger than 0 and less than or equal to 1 on the interval from 0 to pi over 2, like that. So playing the role of little m1 and m2, sorry, this is m2, m1, this is big M2 and big M1, like that. Playing the role of those bounding constants are 1 and 0. And we can immediately now jump to, using this identity up here, that the integral in question e to the minus y cosine x dA is less than or equal to m1 times m2, big M1 times big M2, times the length of the x interval, pi over 2, times the length of the y interval, also pi over 2, and that works out to be pi squared over 2. Sorry, pi squared over 4. And on the other side, we have little m1 times little m2 is 0, and again times pi squared over 4, but that doesn't matter, and we get the result that we seek. So again, there's a typo here. The upper bound should be pi over 2 quantity squared. I've reported that to the textbook authors. Suppose f and g are continuous functions, and again, they're positive and they satisfy these upper and lower bounds on the intervals. Let's show that the following inequality is true. All right, so slightly different inequality. The previous one was the product of f and g. Now we're looking at the sum of f and g. All right, let's see how this is going to go. We can take the integral. I'm just going to use r because it's quicker. The integral over this region of f of x. So that's equal to the integral over the region fx dA, and the integral over the region gy dA, right? Cool. And we can do, because this function is independent of y, we can integrate it with respect to y. So let me rewrite this. C d a b f of x dy dx plus a b c d. Notice I'm switching the order of integration. G of y dx dy, switching the order of integration. And observe in the first integral that the integrand is independent of y, so I can do the inner integral just as f of x times y, and then evaluate that from c to d, and that just turns into d minus c. And similarly, the second integral, the integrand is independent of x, so I can calculate that integral, the inner integral, as g of y times b minus a dy. And that's about as far as we can go with the y integration or the x integration. Let's see, we get in the first inequality, so this is equal. This is going to be less than or equal to, what's the upper bound for f on this interval? It's capital M1 times the length of the interval. And then this is a constant that just goes along for the ride. And then the second integral, g is bounded above by capital M2. And then the integral is bounded above by m2 times d minus c, and then the b minus a goes along for the ride. And we get exactly what we expect here. We can factor this common factor out of both terms and end up with the exact result. I'll leave it to you to figure that out and to try your hand at the lower bound. Okay, once we've established this identity for bounds on sums, we're again going to try an exercise that applies that result. So here we have the sum of two functions, one solely of x, one solely of y, on these two intervals, pi over 6 to pi over 3, pi over 6 to pi over 3. And we first get some upper and lower bounds for sine and cosine on these intervals. We know, for example, that the sine of x is between 1/2 and root 3 over 2 on the interval pi over 6 to pi over 3. And similarly, we know that the cosine of x is between those two values on that interval, right? Okay, cool. This gives us our little m's and our big M's. And this gives us our intervals, and we're kind of ready to go. We have all we need to approximate this integral. The integral over r of sine x plus cosine y dA is less than or equal to the sum of the upper bounds times the length of the y interval times the length of the x interval. What's the length of one of these intervals? It's pi over 3 minus pi over 6. That's 2 pi over 6 minus pi over 6, aka pi over 6, right? Pi over 6 here, pi over 6 here, because they're both the same length interval. And where are we? We have root 3 times pi squared over 36, and that's precisely the bound that we have for the for this side. I'll leave it to you to figure out the lower bound, but hint, hint, it's going to rely on these little m's. 1/2 plus 1/2 is 1, and you're going to end up with pi squared over 36. All right, another theoretical one, problem 52. You're given this strange looking double integral and you're asked to show that it's equal to this equally strange looking collection of symbols. Let's start at the beginning here. We can rewrite this. I'm going to separate this into two pieces. An integral of y f of x and then an integral of x g of y. So we go a to b, c to d, y f of x dy dx plus the integral from c to d, a to b. Notice I'm switching the order of integration, x g of y dx dy. So I'm allowed to change the order of integration. It's not going to change the integral, and I'm allowed to break it up by that list of properties up above of double integrals. Why have I done this? Well, it turns out I can actually integrate with respect to y here, and the f of x has no impact because it's a constant with respect to integrating along y. And so I'm going to do this y integral. We get y squared over 2. We plug in d, we plug in c, and we subtract. And we get 1/2 d squared minus c squared. And what's left is the integral in x, which we can't actually do because we don't know what f of x is. Similarly, here I can integrate with respect to x. This is a function of y. It's a constant. I get b squared minus a squared, and then what's left behind is the y integral, c to d, g of y dy, and lo and behold, that's precisely what we have up here. So the key here was noticing that if I broke the integral up, I could actually do the y integration for this term and the x integration for this term, and then I get the expressions that I expect. All right, in exercise 57, another theoretical question, you're asked to show that the average value of a function on a rectangular region is given by this expression. This is a pretty common formula in application. You see it come up in statistics quite a lot. Let's see how we get to this expression. So what we see is on the left-hand side, the integral average. Let's start with the definition of the integral average as 1 over the area of the region times the integral over the region of f of x and y dA. Now, there aren't too many ways to move forward here. Probably the most direct way would be to replace the double integral with a double sum, or approximate the double integral with the double sum. So we'll keep that area term, and we'll replace this as the sum. I equals 1 to m, j equals 1 to n, f of xij, yij. These are the sample points we're not really specifying midpoint, upper left, lower right, etc. We're just assuming we've got some kind of sample point here, and then times the area of each of the little subrectangles. All right, if you'll remember, the area of one of the little subrectangles is just b minus a over m times d minus c over n. And that simplifies to, well, let's just leave it. It doesn't simplify that much, honestly. All right, so noting that delta, that the area of one of the little subrectangles is given by this, and recall that the area of the rectangle is just b minus a times d minus c. Notice what happens when we take delta A and divide by the area of R. The b minus a, d minus c terms cancel, and what we're left with is just mn in the denominator. So if we do that, we can rewrite this double sum as the sample values of the function. And we can just put 1 over mn out front. And that is the desired formula. As an application of this new formula, we're given a temperature map. This is something that you might see on the Weather Channel site or something like that. It's the temperatures of all the weather stations over this particular region of the country. And you're asked to use the formula that we just derived with the midpoint rule and m equals n equals 2 to find the average temperature over the region in this figure. Okay, we're supposed to divide this up into 2 subintervals in the x direction and 2 subintervals in the y direction. Let's sketch those in to the figure. So just dividing this by I in half vertically and by I in half horizontally, we get the partition that we are asked to look at. Let's put, we're using the midpoint sampling rule, so let's put eyeball some points sort of in the center of each of these regions, here and here. And I'll just arbitrarily label them 1, 2, 3, and 4. And if we go around here, we see that 1, looking at the data on the graph, 1 is approximately, looks like I kind of overwrote that, okay, around 36. 2 is sitting right here on top of the 43. 3 down here in the lower left, somewhere between 71 and 72. It's closer to 71. Let's just use that. And finally 4, somewhere between 70 and 80. And along this line, if we assume it's sort of going linearly, let's call it a 72. All right, those are the 4 sample points. We add them together and we divide by m times n, which is 4. M times n is 4. And I took the liberty of calculating that in advance. Let me go find that. That's around 55 degrees. So the sum of these guys divided by 4, we get an average value of around 55 degrees. This is yet another example of how we use Riemann sums in practice. We don't usually have functions that describe for example, the temperature at some moment in time over the United States, and so we're left with sampling data, and the Riemann sum provides some really practical ways of getting at these theoretical quantities. Suggested exercises, essentially all of the exercises at the end, I want you to work through a sampling of them from each of the sections at the end, and make sure that you kind of get a grip not only on computing these things, but on doing the applications and the Riemann sums. Again, there's a link to the Sage worksheet that does the Riemann sum approximations. I want you to download that and then upload it to Sage and use it for your own calculations. When you feel like you've got that all squared away, head over to WebWork and try Chapter 5, Section 1 assessment. Thanks.